So I'm really happy to be with you, and I'm sorry I can't be there in person in the room. Uh, I think a lot of the things I'll say are quite similar to the things that you just raised in the session with Emily. So I will more or less be repeating things that you've already said, which is nice because it means I'm talking to people who have a sort of similar view. Um, so the Quantum Energy Initiative is a very informal organization. It has no official budget and no official real status. It's just a community of people who came together thinking that they wanted to encourage other scientists and engineers to think about these questions of the energy footprint and the environmental footprint of quantum technologies. So we came together, I'm losing track now, about 2 years ago. We organized a workshop last year in Singapore, and we're organizing another one to discuss the science of the energy footprint and resource consumption of quantum technologies. We're organizing the next one will be in January in Grenoble. And I realize I didn't put that on a slide, so I'll can mention that again at the end if anyone's interested in the details. I can maybe put the link in the chat. Yeah, the idea is that while we all hope that quantum technologies will be useful for society and bring good things to society, we also know that any technology has a cost. And right now, we know that environmental and energy costs are critical for society, for if we want to have a sustainable society. So we think while we're not trying to take anything away from people doing research to make quantum technologies work better, we think it's also important there are people thinking at the same level of, detail about how to make quantum technologies work with less resource consumption. And we think those are interesting scientific questions to which we don't know the answer. And so they merit to be studied. And so that is our main goal, is to create a community and environment on that around that subject. And then, of course, there's also the connections, broader connections to social scientists and civil society and politicians and stakeholders and all of these people, which I might come back to towards the end. Why my slide's not going? Okay, so I just thought I'd mention, I think everyone in the room, from the responses I saw, you all are reasonably expert on quantum computing and quantum technologies in general. Probably many of you know much more than me. But I have this slides that I often show to people who don't know much about quantum computing. And basically it's the idea that quantum computing, and you can say other quantum technologies as well, although one of the perhaps weaknesses of the Quantum Energy Initiative right now is we're a bit too quantum computing, and we would like to open out to all of the other quantum technologies. So we're trying to do that. But so the point of a quantum computer is it's all about noise versus resources. If you want the computer to work, you have to fight against noise, because we know noise destroys quantum states very easily. They're very fragile. And you have to put in resources to fight against that noise. And there's a simple, silly analogy I can make. So is that you shouldn't be thinking about a computer like we're used to, like on our laptops or whatever. You should be thinking about something completely different, which is a group of parents trying to have a serious discussion in a children's play area. So the children are running around making a lot of noise, and the parents are trying to have a serious discussion. So in this context, the qubits are the parents, who are the quantum degrees of freedom that you're using to do something useful. And all of the other quantum degrees of freedom around are the children who are running around, living their life, having fun, but are not, and are interfering with what the parents are trying to do to have their discussion. So this is the image of a quantum computer, which I think is maybe closer to reality than the normal computers we think of every day. And then you can even go even further and say that the children making a lot of noise are giving their parents all migraines, so that their parents are also forgetting what they're saying. You know, it's the idea that a qubit forgets its information. So that's a sort of very silly sort of analogy, which I think helps maybe against quantum, the sort of quantum hype that we see, where we say, you know, we imagine that because we know how to build traditional computers, we also know how to build a quantum computer. And it's just a question of time and money, and we will have a quantum computer in 5 years. You know, I think most people in the domain they have optimistic days and pessimistic days, and on pessimistic days, they're not sure we will ever have a working quantum computer that's big enough to be really useful to do things. And on optimistic days, we think, yeah, we probably will in a few years. So that's the situation. And so then we can be a bit more scientific, a bit more precise about things, and we can say we have some machine, and that machine has imperfections, that is the noise. You need to put in resources to make the machine work, energy and materials, and then you have some target performance. And so typically what we have in mind is that you want to minimize, you have a given target performance that you want to achieve, and you want to minimize the resources you put in to achieve that. So it's a minimization problem in the context of the imperfections that you have, the noise that you have in real life around real qubits, and the different ways you can put in resources to control that. So the job of science, I guess, is to understand the noise, the resources, and make the connection with the target performance. The job of technology is then is when it looks like it should work, it could work, is then to increase the performance and reduce the resources. So, and the role of society then is to say, well, what applications are worth the resources that we're investing? So I think that's something I'll come back to at the end. Maybe it's not something that scientists or engineers should be making the decision about, is if there are clearly things that if the machine, for example, could develop new medication or help develop new medication by simulating molecular dynamics in some clever way, that could, you know, I don't know, treat cancer or treat malaria or something like that, then probably society's judgment of how much that's worth in terms of invested resources is clearly much better than if it's just a better way to put cat photos onto Instagram or something like that, right? So clearly what you're trying to do makes a huge difference for society about how much resources we should invest. But those decisions, I don't think, really can come from scientists or engineers. They have to come from society in a broad sense. And of course, we're all part of society, so we should all have our opinion on it. But our opinion shouldn't necessarily count more than you know, anyone else's. But that's also a discussion. Should scientists' opinion on these technical subjects count more than someone else? That's also an interesting question. So where are we now with quantum computing? Well, if you want to make another fun little analogy to another technology, we can think of the technology of flight. So if you look where we are now, a traditional computer is like a big jet, and a quantum computer is like a paper aeroplane. And I think also in terms of resources, right now, if you look around the world at all of the quantum computers in the world, their resource consumption is absolutely tiny compared with all of the jets flying around the world. So that analogy is, in terms of quality, the quantum computers are not yet able to compete with traditional computing, but also in terms of the resources, they're minuscule compared to other things. But now if we look at the trajectory, of course, so I've put a timeline here, things are looking different. So if you look at classical computing has been quite stable since the 1960s or 70s, incremental improvements every year. So, you know, even Moore's law, so growing exponentially, but in quite a stable way. Now it's flattened off people saying Moore's law is no longer being followed for a good few years now. So things are sort of reasonably stable, a bit like flight, and a big airliner from like a 747 from the 1960s and a modern airliner don't look that different. In contrast, quantum computing, in the at the end of the last century, we had the basic building blocks, but we didn't really know what to do with them. In the last 15, 20 years, we've started to build up to make the ingredients that we need to build a quantum computer. And now we're starting to build the first quantum computers, but they remain fragile objects that are not really necessarily useful for anything. So I think the paper aeroplane is a good analogy. But then, of course, you see that trajectory and you say, okay, well, what does that mean for the future? So if we are optimist, maybe we will have something really futuristic in not a very long time. Or the other possibility, of course, is that we get stuck at the paper aeroplane stage with quantum technologies, that we don't ever get something that's really useful for anything. And I guess it's just too early to say. And of course, lots of researchers are working hard to make things work. And, I would like that the things work. But of course, then the question is, if we consider resources now at this stage and make things energy efficient from now, then will that help the trajectory towards any future technology that emerges? So that brings me to the next slide. So various claims have been made in the literature, and that's what started us on this trajectory. Is we found people claiming, usually in anecdotal ways, that either quantum technology would have a huge energy consumption or that it would consume way less than traditional computers. And so the answer is now our team has started doing research on that, and Marco will talk about that, I guess, just after me. And other people have started doing research on that as well. We're using different methodologies, looking at different technologies. And the answer is we don't know yet. We don't know what's going to happen, but it's clear that the research will help us and help us get on the right path, if the right path is available, of not consuming huge amounts of energy that maybe society doesn't have. So the main thing is that means that we need methodologies. We need objective ways maybe to compare things. So we need objective ways to compare. So we talk about figures of merit, but an objective way to say, to compare a traditional supercomputer and a quantum computer, both in terms of what their output is, in terms of what we get, and also in terms of what we invest, in terms of energy and materials and so on. And we think that this is perhaps the first time we're so early in the evolution of a technology, even before when it's still more or less a science and not necessarily completely a technology, when we can think about the fact that resources are finite. I think with the last big technological revolution, that you might say something like artificial intelligence, still in the early days of it, like, I don't know, the 1960s, 1970s, people weren't yet really thinking about the fact that resources were finite. And now we know resources are finite, and it's a big impact on our daily life, or at least it should be. And so it is good to also be thinking about the development of the technology and the development of the science in that context. And the other thing is we need to build an interdisciplinary community to address those questions. And develop common languages and tools. And so that's what the Quantum Energy Initiative is trying to encourage, this idea of getting people together with different expertise so we can discuss the topics and develop a sort of common language and try and understand each other's methodologies and understand each other's problems. And we often take a picture like this of the full stack of a quantum computer to show why we need so many different communities. and this is a sort of simplified version, simplified picture of all of the things that are in a typical quantum computer. And you can probably make a similar diagram for any other quantum technologies. So if you like, at the top, we have a lot of computer science. People think about algorithms and compilers and error correction methods. So that's close to the end user of any computer that we build. And then as you go down the stack, you get into the actual physical architecture. So you have all of the qubits and all of the control electronics that control the qubits, which are mostly quantum physicists thinking about that sort of thing. And then at the bottom of the stack, you have all of the technologies that you need, many of which are quite classical rather than quantum technologies, like cryogenics, microwave generators, lasers, and all of these things. Some of them are quite new, some of them are quite old technologies or mature technologies, but all of them have a big contribution to the total energy cost of any quantum machine. And so somehow what one needs to do is one needs to make sure that the people who develop, for example, the cryogenics to keep the qubits cold are talking the same language as the people who actually write the algorithms to run on the quantum computers, so that we know how to optimize the global system to minimize the energy consumption, right? Because the output of the computer, if you like, is at the level of the algorithm. You know, it will give you an answer to the question that you ask. That you ask the computer a question, it gives you an answer, and you want it to give the right answer. But all of the resources, at the macroscopic level, are all at the level of cryogenics, control electronics, and all of these things. So one needs to make a clear connection between the two if you want to minimize the resources without impacting the outcome of any calculation you want to do, without impacting the quality of the quantum computer. So one thing I think that's nice about this, which is a small side note, is that it's about doing more with less. And it's a good subject, I think, for small teams with maybe smaller budgets and less equipment. You know, if you want to compete to build the biggest quantum computer or the most powerful quantum computer in the world, then you need a huge budget like Google or Microsoft or whatever. But if you want to bring something to quantum technologies that will be useful, it could be to optimize a little component in that would be used in a quantum computer. You know, think about how to make, I don't know, a particular amp needed in a quantum computer, how to make it more energy efficient, or think about optimizing the controlling qubits with slightly less strong drive signals or something like that. And those are the sorts of things that can be investigated by a relatively small team, and they can do interesting, useful work on the subject with a small team with just maybe one qubit, or even without any qubits in their system. And you don't need to be competing directly with the big companies or big institutes. So then the quantum energy initiative community. So we have a board of whom a few of us the co-founders, and then we formed a board to try and broaden out our expertise. We're still, as I said, a little bit too much quantum computing, and we lack a little bit in quantum sensing and quantum communication and things like that. But it's a bottom-up initiative. We want to build things, and we think it's important that these energy issues, in the limit of what's possible, should be treated as open science, so that we try and build on publicly available data and try and analyze publicly available data. And we try and encourage companies to be as open as they can be about the energy consumption of their devices and how they could be improved and what the challenges are for them. Of course, we understand that companies also have to keep a certain number of secrets, but that's life. So we try and organizing concretely. At the moment, we're mostly organizing workshops. Trying to organize one every year, and encouraging other people to organize workshops like this one today. And we also have a YouTube channel where we put talks, so you can look at the YouTube channel. And I just realized I didn't put any links on the slides, but if you type Quantum Energy Initiative into the YouTube search thing, it will find it. If you type QEI 2025 into Google, I think it will find, and if you add the word Grenoble, it will definitely find the workshop website, which is quite empty at the moment, but you can bookmark it and come back later. It should be being filled up over the summer with a list of invited speakers and opening for submitting abstracts. And we have a bunch of companies and institutes that have shown interest. So it's quite a long list, and this list may not be up to date. And there's probably a few that are missing. But we realized that we're definitely not the only people who are thinking about this. And there are plenty of people who haven't necessarily aren't on this page who are also thinking about these questions. And you, I see, are also thinking about these questions. So this is all good. And now if we just come back to what I'd say goes a bit beyond what the Quantum Energy Initiative is aiming to do. Our main aim is to try and bring scientists and engineers together to make quantitative evaluations. But then there are obviously questions for society in general, which probably when I talk to social scientists, it's the sort of thing I would like them to help us understand, which is how do we judge when something is worth the resources and in the environmental costs? Should it be quantum scientists and engineers who decide? And I would say, this is my personal opinion, I said it shouldn't be us who decide. We could, of course, contribute to the discussion. Should it be a market economics that decides? Should it just be the price of, if people are willing to, if consumers are willing to pay for whatever it is, then we decide that it's good. And if consumers aren't willing to pay, then we could decide it's bad. I think many of us would feel that's not the right way forward with the current environmental crisis. Should it be universities that decide, military, governments, these sorts of things? And then, of course, that's the question of resources, but there is also a question of, there are also a bunch of other questions like the security arguments versus the openness of knowledge with quantum technologies, particularly if quantum technologies have an impact on secrecy, either having quantum communication to have ultra secret communication, or having quantum computers that might one day break encryption. Although I think now the experts are now understanding that's a long way off. A quantum computer will do many things that are useful before it will be able to break encryption. Although I'm happy to hear people who disagree with that point of view, because I don't think it's completely clear yet. And there's also a question for governments is about new rules, not just laws, so maybe not just governments, but for society in general, also voluntary codes and so on, that would avoid any abusive use of future quantum technologies. And of course, always the challenge is, while the uses of the technology are not clear, it's hard to do all of these things. With artificial intelligence, we're much further ahead, and still we don't really necessarily know how to put in place a good governmental, a good legal or voluntary framework for artificial intelligence, because we're still not really sure what it can do. So for quantum computing, we're way ahead of that, but I think it's good to start thinking about these questions from the beginning, because in the past, it has been rare to think about these questions early on in the development of a technology. And of course, there's a question of what are the blind spots of quantum scientists? What are things we haven't even considered that will impact society and our future? So with that, I think, yep, that's the last slide. So maybe I leave those up, or maybe I'll skip back to the Quantum Energy Initiative actions. Yeah. So thank you very much.
The room, we can ask questions either just put your hand up traditionally, or also on Menti if you want, like anonymous, or to sort of add a queue of questions. be able to read them out to Rob. And then also on Zoom, there's the Q&A or the chat function also meant to ask you as well, or just, yeah, shout out and raise your questions. Yeah, go ahead.
I don't hear anything. Is someone asking? If someone is asking a question, can you maybe repeat it closer to the microphone?
Yeah, can you hear better?
Yeah, that's perfect. Thank you.
Hi, you talked about comparing the quantum computer with something like a supercluster computer, and I wanted to ask you how you in principle could compare them, because yes, there are problems that, for example, also a supercomputer could solve in let's say a little bit more time than a quantum computer that would work, but still you maybe could compare the energy consumption of both, but how do you compare them and say then, okay, it's not worth it to develop the quantum computer for something like that?
Mm-hmm.
Do you get my question?
Yeah. I think it's a really good question, and the answer is I don't think we know yet. I think we still. So of course I have my opinions about this because I've thought about it quite a lot, and Marco, I guess, will present one aspect of that just in a few minutes, but which was the work we did together. I think the question, so I'll limit myself to say I think it's a really good question. How do you compare? So if you're comparing two different traditional computers, you can just count the power. There's this sort of green 500, it's called, which is supposed to the 500 supercomputers that are the most energy efficient in the world. And they typically talk about the power consumption per flop or something like that, right? Quantum computers are so different from classical computers that you can't compare energy per gate operation or something like that. You really have to compare probably at the level of the problem you want to solve. So you have to say, I want to, I don't know, simulate this particular molecule that might be useful in some medical treatment. I can either simulate it on a quantum computer or on a classical computer. What is the energy cost for a simulation of similar quality? So the question of the quality of the simulation is clearly critical because both of them introduce errors. Classically, usually because you make approximations in the simulation. In quantum computers, you may make approximations, but also the quantum computers are naturally noisy, so they will always have some error probability. So you need to fix what you want, with what precision you want it, and then once you fix that, maybe you can make a fair comparison between doing it on a supercomputer and doing it on a quantum computer. But that one needs to be quite careful about. And actually, I should mention something I didn't say was, I should have had a slide on it, was at the IEEE, we have created a working group which anyone can join to discuss exactly this thing about how does one quantify, or how does one come up with a benchmark of quantifying what the energy consumption of a given technology is, quantum technology versus maybe classical technology, also between different quantum technologies. If you have a particular quantum technology, I don't know, superconducting qubits versus cold atom qubits, for example, can one benchmark them on a way that's fair to both or realistic to both and say, okay, this particular machine consumes this amount of energy to do the same thing as another machine of another technology to do the same thing. But I think all of these questions are open.
You didn't mention time. I know that this here primarily this workshop is about saving energy, but shouldn't be time also a very important part? Because I can imagine if we're, let's say, we want to simulate a molecule, then maybe let's take a cross difference. The supercomputer takes 1 week and the quantum computer takes 1 day. Should that be also part of this benchmark, or is that something completely neglectable?
So I think that's also a very good question. I can give you a more, and even, so I think there are particular problems where time is an even more critical issue than, let's say, let's say in the example of simulating the molecule, maybe it's as part of a research project that will last months or years. So whether it takes 1 week or 1 month is maybe, or 1 day or 1 month is maybe important but less critical. There are also time critical things. If you want to, for example, be optimizing a transport system in real time, then it's really important that if you want to avoid traffic jams by rerouting cars, if your calculation on your classical computer takes 1 month, it's already too late. So there are clearly cases where it's important to have real-time results very fast. So I think time would also enter into the game. I think energy, perhaps for the sorts of things like simulating molecules and things like that, maybe energy would be the main one, because in principle, if it's much more costly to do it on a quantum computer, in terms of energy, even if it's faster, probably it's not worth it, because you can always imagine having many supercomputers in parallel and running many simulations on them to get the results of your research project faster. And if having many supercomputers in parallel still costs less energy or less resources than one quantum computer, then the time gain is maybe in that particular case not so relevant. But I think in general, the time would be another very critical parameter. Yeah.
Thank you.
Questions? Yeah. Coming up to the mic.
Hello, thank you for your presentation. I wanted to ask if you already have any use cases where the Quantum Energy Initiative made some improvement to quantum technology?
So probably not yet, or if there is an improvement, it's a very small one, because we're quite new and our main goal initially is to get people to talk to each other. So if we have made an improvement, it's because someone talked to someone at our workshop, or someone who listened to one of our online YouTube videos had a good idea and implemented it in their own technology, maybe without us knowing about it, right? And I think that's the most important thing of these sorts of networks, is to have informal ideas circulating that make things better, but you can't really say, oh, we did that, right? It's a way just to get people to think about maybe problems in a different way from they were thinking about them before. So I would like to think that we're already starting to have an impact, but we may never know. And for me, that's fine, right?
I see, thank you.
Mm-hmm.
I have a question as well then. So you said obviously the QEI is bringing together the community of researchers, and you already had the first conference in Singapore and you have the next one coming up in France. I was wondering sort of if you see any gaps in the people that you've brought together so far already, and more who you kind of want to address going forward, or any sort of gaps going forward that you want to fill.
Yeah, I think I would say there are more gaps than people right now, in the sense that we're starting with people who are willing and interested, and who sort of volunteered to come and join. and perhaps also that we know in our personal connections. So that means we're too quantum computing focused right now. We're probably too focused. We may also be too focused on low temperature qubits, so superconducting and spin qubits, and so those are the subjects where we have found a lot of people who are interested in energy consumption because they see it as maybe also as a short-term problem, because when you have cryogenics, what you can actually put into your, you have to buy a bigger cryostat, which costs a lot of money if you want to put more things inside, or you can keep the same one you have and try and do things more efficiently. So I think even on short-term scales, that has a natural attraction to people. But that means we're really missing people. I would love to know more about quantum communication and what the energy implementation or consequences of quantum communication are. We have a little bit of people from quantum sensing, but not enough, and other quantum technologies as well. So yeah, we're open and we're trying to grow and we're trying to cover all of these things, but definitely many things are missing, and we would love to have more people with more diverse opinions and more diverse areas of interest.
Very interesting. Thank you. Nice. Does anyone have any questions right now? Because otherwise we could sort of discuss that quickly, that obviously the format of today means that those who are already interested, and as we saw from the mentee earlier, everybody here is interested and wants to get informed on this. But then you yourselves, if you're talking with other people, do you know where other people are standing on this and how we could get them involved, how we could address other people that aren't here today?
So, okay, maybe I'm the only way I know how to do things is more or less how you're doing them today, which is to organize events, advertise them, and get people who are interested to come. And while we can, I guess while we can continue to grow doing things like that, I guess that's the most efficient. But that may be me having my own blind spots about more intelligent ways of acting. The thing is, as we want to be we should be clear that we want the Quantum Energy Initiative to be a community of people thinking sort of quantitatively about these questions. We don't feel like our job is to be a pressure group necessarily. It may be that we need to create some other structure that would be more of a pressure group and more talking to politicians or society. So we do a little bit of that, but let's say our core is to try and bring scientists together to have serious scientific discussions or serious engineering discussions, and to create that community within the academic engineering world, because we think that's the most urgent. When we start to have clear predictions that we can sort of validate, then that's the time perhaps we need to move more into pressure groups for change, if we feel we're on the wrong trajectory. But I think the first thing and the main thing that we're trying to do is really be quantitative and understand what is happening in terms of resources for quantum technologies.
That's really interesting.
Out of interest, could you imagine to do something like the In a Nutshell channel in YouTube? So you're making short videos about the topic. For example, the photonic quantum computer has disadvantage in matches for energy saving and resource saving and something like that. Maybe that is something.
Yeah. I think that's something that, I would encourage all members of our community, when they do a piece of research, I guess, on a particular topic, on a particular technology, on a particular way of implementing the technology and its consequences for resources, then I think, you know, it's important to do outreach on the results of the work. Perhaps when we start to see a bunch of works appearing, perhaps, you know, being scientists, my temptation would be that we first write some sort of review article or have some sort of special issue of a journal, and then off the back of that, do things that are a bit more drawing attention of the public or of other scientists to that, but where there's a core where people can go and look and see hard facts, right? I think that's what's important. Otherwise, we just get into the question of hype with, you know, one person saying quantum technology will save the planet, another person saying quantum technology will destroy the planet, and we don't really know what to do, how to make a value judgment on those two claims unless we have some sort of hard facts. So I think first we need to do the research, and then we need to think about how to disseminate it. But yeah.
Okay, thanks.
Mm-hmm.
Does anyone else have any other questions at the moment? Rob, would you be able to send myself the presentation that you had? Because I think you had interesting questions at the end we can discuss together later.
Yeah.
Thank you.
Okay.
But then, then thank you kindly for being here today. It was really interesting to have your overview of the QEI and the nice introduction. So.
Okay, good. Well, thank you for the very nice questions at the beginning, because I think in some sense what I said and what was your responses already in the room to the questions were extremely similar. So I think
nice to hear it. We're aligned.
we're all in a similar state in our thinking and in our evolution on this subject. Yeah.
I think so.
Okay.
And nice.
Thank
and
you.
amazing. Okay. Catch you later. Thank you.